everyone. My name is Declan. I'm an undergraduate student at Northwestern University, and I'm very excited to be here today to talk about my paper, trying to model baseball using transformers. So I'd just like to start off with a little bit of the motivation and goals behind this project. So I think one of the most important and also interesting parts of baseball is the decision of what pitch to throw next, and really what makes it so interesting. Just how complex of a decision that really is. And so when a player or coach is making that decision, they have a whole bunch of different factors they need to take into account. They need to take into account the current pitcher, what kind of pitches do they throw, their moment-to-moment command with each of those pitches. You need to consider the current batter's hitting style, their previous at-bats in the game. And then you also need to consider just the game situation as a whole. And so all of that also has to be done in just a matter of seconds for each decision. And so because of that, it's really impossible for a human to perfectly take into account all of those factors when making that decision, hundreds of times in a game. And so because of that, I think it would be really useful to have some kind of a system that would be able to perfectly keep track of all those factors to make pitch recommendations and do this in real time. And so that was the primary goal of this research, was to try and create a version of that system. And so we're going to approach that goal by trying to create a model that does single pitch prediction. And that is, we want the model to be able to answer the question, what would happen if this pitch was thrown next? And so if we can create a model that does pretty well at that task, we could then use it downstream in a framework to actually find optimal pitches in a given scenario. And so we're going to try and do that first by modeling baseball as a sequence of pitches, and then using a transformer-based prediction model to directly predict the outcome one pitch into the future. And once we have that model, we can then use it to simulate potential pitches that can be thrown in a given situation and rank them based on the model's predictions. So getting into a little bit how we're going to do that. Starting off with just how we're modeling the data. Like I said, we're going to be modeling baseball as a sequence of pitches. And so what a single one of those pitches is going to look like is an 87-dimensional vector. And it's going to contain both continuous and categorical features about said pitch. And that's taken from the StatCast data set. So it's going to include things like the velocity of the pitch, spin rate, what kind of pitch was it, things about the current situation in the game. And then it's also going to include things about the outcome of the pitch, so ball, strike, single, double, et cetera. And so downstream, the model's task is, for one of these pitches, it's going to be trying to predict those outcome-related features. And so because of that, we're also including certain mask dimensions so that the model doesn't actually know beforehand what those features are going to be. And so how we're actually going to create the sequences of pitches that we're going to use to train the model is basically we're just going to go through a StatCast data set and group all the pitches based on the current batter and order them chronologically. And we're then just going to use a simple sliding window approach on each of those groupings to create sequences of 400 consecutive pitches. And so the model is going to be able to take one of these sequences as input, and its goal is going to be, for the final pitch in that sequence, predict the outcome-related features. And so just a little bit of why we're actually going to be using transformers for this task. And in case you're not familiar, transformers are just the kind of model that are used in things like ChatGPT. And so really one of the main reasons is because the order of pitch sequences is really important. And so if we just look at these two examples of a pitch sequence, fastball, fastball, low and away slider, your first intuition when looking at that is probably going to be, okay, the pitcher got ahead in the count and is now trying to strike out the batter. Whereas if we just reverse those, your first intuition is probably going to be the pitcher got behind and is now trying to catch back up in the count with 2 consecutive fastballs. And so the main idea here is that the order of the sequence, despite having the same kinds of pitches, is going to influence the way you interpret them. And so because of that, we want our model to be really good at understanding that order. And that's exactly what transformers are good at doing. They're good at looking at sequences and learning and recognizing patterns within them. And then just additionally, transformers are going to let us use a much larger context window than other kinds of sequential models. And so just a quick look at the diagram for the model architecture. Like I said, we're starting with an input sequence of 400 pitches that's going to be processed by the model, and then the model's job is for that 400th pitch to predict the outcome-related features of it. And so that's going to include things like the exit velocity if the ball was hit, It's going to predict a probability distribution over potential hit outcomes. So that's going to be like whether it was a strike or ball, single, double, et cetera. And then another probability distribution over potential hit locations. So that's going to be things like second base, shortstop, center field, that sort of thing. And so, yeah, we went ahead and trained this model using that single pitch prediction task. And for the training data set, we're creating just a bunch of those 400 pitch sequences using the 2015 through 2022 MLB seasons. And like I said, the model's job is taking in one of those input sequences, predicting the outcome-related features. And just a quick look at the loss function that we use, you'll notice that we're weighting more heavily the model's predictions over the probability distributions based on outcome and hit location, just because those are what we're going to be using when we're actually selecting optimal pitches. And we're mainly including the continuous prediction task over things like exit velocity just to aid in the model's overall understanding of the game. And so looking at some of the results and evaluations that we did. So first, just going over some of the models that we looked at. So one is just a really simple historical average baseline based model. All we're doing for this is finding an average pitch outcome distribution from the previous season. And then when we're making predictions with this model, we're just going to be sampling from that distribution. Next is just an XGBoost model. So this is a bit more complicated. This is going to be trained on the same feature set as our transformer model is, except it's not able to take in to account the sequential information like our model is, and of course the transformer model. And so the first metric that we're going to use to evaluate this is top K precision. And so this can be thought of as just a measure of how often the true outcome is among a model's top K predicted probabilities. And so this makes sense to use in our case just because of how imbalanced the outcome distributions are. If you think of, like, for a single pitch, 95% of the time the outcome is either going to be a ball or a strike. So we can't just rely on something like prediction accuracy. And so using top K precision is going to give us a better overall understanding about the quality of the probability distributions predicted by our model. In our particular case, we're setting K equal to 4, with the main rationale behind this being ball and strike are pretty much going to be in the top 4 predictions every time just because of how common they are. So it ends up being closer to around K equals 2. And so looking at the 3 models' results on this, for this top 4 precision, this is for predictions over pitch outcome. Just a quick example of how to read this table. If we're looking at, say, the singles row, when a single is the true outcome of a pitch, the historical average baseline is going to have it in its top 4 predictions 35% of the time, XGBoost 86% of the time, and the transformer model 97% of the time. And so the main insight to gather from these is that the XGBoost and transformer model, pretty much all the models actually, are really good for common outcomes like ball, strike, and field out. But the difference between the transformer model and the other two is that it's going to do a lot better for the more rare but important outcomes like single, double, and home run. And again, same metric, except this is for the predictions over hit location. I'm not going to spend much time on this just in the interest of time, but overall the transformer model does the best out of the 3 on this task as well. And so another thing that we could also evaluate these models for is their player adaptability. And that is, are they able to alter their predicted distributions based on the current batter? And this is obviously going to be really important if we're going to be using these models to try and recommend pitches. And so how we're going to do this is we can look at 2 different players that have a very different hitting style. In our case, that's going to be Judge and Luis Arias. And so what we could do is, for a given season, we're going to predict the outcome probabilities for every pitch that they've faced and aggregate them to get an expected event count for each type of outcome. And we can then compare that to the actual counts they had to that season. And so when we do that, we get these 2 tables. On the left, we have Arias, and on the right, we have Aaron Judge. And so the insight to gather from these is that the transformer model is actually able to learn about that player's unique hitting style and adjust its predictions based on that. So if we look at the strike row for Arias, we're going to see that it's actually predicting far fewer strikes than the other model. And so this is kind of giving us a sense that the transformer model is able to understand that for an average hitter, a lot of these pitches would be strikes, but Arias is much more likely to make contact with them just because that's his hitting style. He's a contact hitter. Likewise, if we look down, it's predicting far fewer home runs for him, far more singles, far more field outs, and very few strikeouts. And so that idea that the model is learning about the player style is also reinforced if you look at the table on the right, where it's predicting Aaron Judge to have around 26 home runs. So it's really understanding their unique hitting styles and adapting its predictions based on that. And so now I just want to quickly introduce how I imagine this sort of model might be used in practice. And so remember, the initial goal was to try and, for a given situation, come up with a set of pitch recommendations. And so we're going to do this by, in a given situation, we're going to take the current batter's previous 399 pitches, and then we're going to simulate a bunch of the possible pitches that could be thrown in this scenario with the current pitcher. And all we're going to do is we're going to take those 399 pitches, add on one of the pitches we're simulating, and run that through the model. And then once we have the model's predictions on that, we could use just a simple formula to try and create a score for each of those pitches. And so in our case, we're just going to use a very simple weighted sum for our score. There's going to be a term that's trying to maximize some desired outcome that we have, so think like strikeout or field out. There's going to be a term trying to maximize some desired hit location, so like if we're trying to get the batter to ground out or something like that. And then there's also going to be a negative term that's trying to control for some risk, that's trying to minimize events that we don't want to happen, like a home run. And so just the process of what using this sort of framework would look like. We're going to start off with the situation. I'm going to say the pitcher is Dylan Cease, the batter is Shohei Ohtani. It's an 0-2 count, and we're trying to get him to strike out. We set our weights for that weighted formula as follows, and we're going to simulate all of these different pitches, run it through the model, score it. And so then after doing that, what we could do is filter to only include the top 5% of those pitches in terms of pitch score, and these are going to be the model's recommendations. And so in this case, the model is saying, or it prefers low and away fastballs to try and strike out Ohtani in this situation. Same scenario, now we're swapping out the batter, so we're going to have the righty Mookie Betts up to bat. We're going to be trying to strike him out. In this scenario, the model is going to give us a different set of recommendations. Low and inside fastballs, and some sliders and curveballs higher up in the zone, which actually might be kind of unintuitive, but there's some data that shows that if you could actually execute a high breaking ball well, it's a pretty good strikeout pitch. Switching up the scenario a little bit, we're going to go back to Ohtani as the batter, but now we're going to try and be getting him to ground out into a double play. So we're going to say there's a runner on first. We're going to heavily weight desired hit location weight to be the infield positions. And so when we do that and simulate all the pitches, these are going to be the top 5% in terms of that pitch score. So it's going to be recommending sliders and curveballs low and away in the zone to try and get Ohtani to ground out. And then just one more quick one for fun. If for some reason you find yourself trying to throw at Ohtani, we could also optimize for hit by pitch. So when we do that, we get a picture that looks like this. And yeah, so just kind of getting into some of the next steps, things I would want to improve upon for further iteration. One would kind of just be incorporating more data. So like I mentioned before, we have some ideal system, and it's able to take into account all the factors. Right now, we're really only creating those pitch sequences based on the batter's previous pitches that they've seen. In the future, I'd want to do a very similar approach for the pitcher's previous appearances, and then also just include a sequence of the entire game up to the point of the current at-bat, because I think that would just give the model a lot more complete context to use when making predictions. And then also refining some of the event classifications. Currently, like one of the outcomes like field out, that's going to be including things like ground out, fly out, line out. So I think breaking those into more specific outcomes is going to really improve a pitch selection framework, and it's also just going to make it easier to evaluate the model's predictions as well. And then finally, just some sort of uncertainty quantification. I think this would be really helpful, especially for the continuous prediction task. We could like the model's predictions on things like exit velocity and launch angle could be very useful for a pitch selection framework as well. So those are just some of the things I want to add. That's all I have prepared. I hope it was all clear. If not, feel free to take a look at the paper. There's a lot more details. But yeah, thank you so much for your time.
Thanks, super interesting. Just a real quick question. On the, when you were comparing to the X Boost, how does it do if you just compare the straight prediction rather than top four?
So it's kind of hard to evaluate because, like I said, we can't really evaluate based on accuracy, because 95% of the time it's just going to be a ball or strike. And if we know beforehand where we're trying to locate the pitch, that's not really a useful thing to predict. I will say, like in terms of like the model's loss, I don't have the exact metrics, but the transformer model does a lot better in terms of loss. But yeah, I think that was definitely one of the challenges as well of this project, was like finding a good way to evaluate the probability distributions that it's predicting. Yeah.
And one more question: how do you? So I guess this is a question about how fast it runs, because in a baseball game you have to rerun it, because if you're thinking about the history of the pitches, your history changes with every pitch. So is this a real-time thing that can?
Yeah. So the bottleneck on that is not actually going to be the speed of the model. It's going to be how fast can we record the data of the previous pitch and use it. But assuming that you could automate that, that's not going to be a problem in practice. Yeah, thank you.
Great job. Thanks for that. Okay, you mentioned like the optimum pitch, for a certain situation, but can that exist, right, in the game theory terms, right? Because I know that that I'm going to pitch, low and away curveball, so I'm going to be looking for that pitch.
Yeah, so that's definitely always something to consider. I think like another one of the motivations for using the batter's previous sequence of 400 pitches is that's including the pitches that the batter has seen in the current game. So like say you're using this model in the third at bat or something, and in the previous two at bats, we have a record of what the pitcher threw in that scenario. So the batter might be thinking, okay, they threw it in this same scenario. They threw this pitch 2 at bats ago, and so I might be thinking, well, they're just going to do that again, or maybe they're going to do the opposite. The model has access to that.
That history.
That history. So if that is something that's important, it finds that as an important in predicting on this task, it'll be able to use that.
Does the model know, like, hey, this is a fresh at bat at this point in that 400 pitch sequence? Because from what I understand, like pitchers, every at bat is a fresh new kind of game, and so the history, maybe the previous 400 pitches don't apply necessarily.
Yeah, so it's not directly modeled, like we're not modeling it like at bats, but it's going to know, like when there's 0 balls, the pitch number is 0, and there's no strikes. It's going to know that it's a fresh at bat. Yeah.
Yeah. Okay. All right. Thank you very much.
Yeah. Thank you.